So let's walk back 13.824 billion years. Now, in principle, correct me if I've got any of this wrong, all of the matter and energy that constitute the current universe, visible and invisible, is collapsed to, well, to a point that isn't even a pinpoint. It's infinitely small and infinitely dense. And there's a cataclysmic explosion.
What is really a singularity? What is infinity? Is it physical or just an abstract concept? The answer is important for understanding the difference between what is science and mathematical laws as abstract models that are written in our own language. It is fundamental for discerning what is real science from pseudoscience and artifacts in mathematical models such as singularities and infinities. In the previous video on the beginning of the universe, I have shown how the Big Bang was not an explosion, but a series of phase transitions described by the standard model of cosmology. The most probable Big Bang theory starts with the first phase transition of a superheated field that forms a microscopic bubble universe that inflates to macroscopic size by a cosmological constant type of accelerated expansion caused by a constant potential energy of a scalar field. It is a period in evolution of the universe called inflation era that occurred at approximately 10 to the minus 34 seconds after the Big Bang. Next, the energy of the scalar field is transferred to the standard model particles by friction, causing the standard hot Big Bang. Only 10 to the power of minus 11 seconds after the Big Bang, at temperature of 100,000 trillion Kelvin, a second-order electroweak phase transition occurs, separating the weak nuclear force from the electromagnetic force. The heaviest particles, such as Higgs bosons, decay to the lightest particles, the electrons and quarks that form protons and neutrons, after which everything is known for the most part: formation of matter, atoms, and structure formation of galaxies. As the universe expanded and cooled down 300,000 years after the Big Bang, hydrogen atoms form, emitting the first light that can be observed as cosmic background radiation. The version of Big Bang theory that most cosmologists agree on is at odds with ideas by Ben Shapiro and Jordan Peterson. Not high-density pinpoints of matter, but an inflated universe that has very small fluctuations in density that were caused by macroscopic virtual quantum particles from the vacuum, from empty space, that were magnified to macroscopic size by accelerated expansion of space. It is even obvious from the map of the universe. The universe is flat. Compared to the initial creation of the microscopic universe, superheated water that transitioned to bubble of water vapor is probably the best way of explaining how can a universe be formed from nothing, from the vacuum. Since the energy of the gravitational field is negative, the total energy of the created universe can be zero. The water is superheated with an energy or temperature larger than the temperature of the transition to water vapor. In such a state, the water is in a false potential energy minimum and cannot transition to a true minimum as a vapor phase. A small impurity or mechanical energy is necessary for transition to occur. A first-order phase transition occurs, which is energetic. Looks like an explosion and a bang, but it is not. Because it happens within a fraction of a second, it is difficult to tell. The Big Bang also lasted briefly, and everything important happened within a fraction of a second. While for the superheated water, the transition is started by a small amount of mechanical energy, Big Bang can be started by quantum effects, where successful transition to a true minimum state is subjected to uncertainty of the field of value. Also, supercooling is a similar phenomenon, which is lowering the temperature of a liquid below its freezing point, without it becoming a solid. Here is an example of supercooled water. The transitions with the slight help of a mechanical energy. Similarly, large-scale structure of the universe had frozen during expansion of space, structures that formed clusters of galaxies. It is an actual mathematical simulation of formation of quantum particles from nothing. We can know that the universe was most probably created by a quantum mechanical process because the quantum fluctuations that are observed in the cosmic background radiation map of the universe, although now macroscopic, have a statistical quantum origin, which implies that the original observable universe before expansion had a finite microscopic size. So the Big Bang was not an explosion, but inflation of space, caused by a scalar field that had an almost constant potential energy, similar to the cosmological constant. I would not blame Ben Shapiro or Jordan Peterson. There is no way you can understand completely the beginning of the universe without years of study of physics on a college level. Physics is extremely difficult. It is what happens when people who have not studied physics try to explain the Big Bang. What is the Heisenberg uncertainty principle? The product of uncertainty in energy and time has to be more than or equal to the reduced Planck constant. Uncertainty between energy and time allows for a certain amount of energy, delta E, to be borrowed from empty space for a short period of time. As an example, a fluctuation in the electromagnetic field can cause creation of an electron and anti-electron pair that lasts for approximately 10 to the minus 21 seconds, after which the same virtual particles will annihilate and return back to nothing. The reason is that the empty space as the lowest energy state, the vacuum, has structure. The amount of structure is determined by the Planck constant, which is fortunately very small, and also the reason why in the classical world we do not detect quantum effects without help of technology, except in some special cases. The vacuum is not static, but a dynamical place where all the quantum fields interact, and every interaction occurs with a certain probability. A perfect example on how metaphysical questions, such as how do you create something out of nothing, that had been subject of futile debates for centuries, cannot be answered with philosophy, but can be answered with physics, and that can be even confirmed by an experiment. Where philosophy fails, science succeeds, a sentiment shared by even Stephen Hawking.
Okay, so that's so interesting, that idea of an infinite expansive potentiality, because potentiality is a very strange, what would you call it, scientific materialist concept, because only what's real can be measured materially. But we need this hypothesis of something approximating an infinite potential.
Infinite potential would imply infinite potential energy. And since mass equals energy, then also infinite gravitational interaction. The whole space would collapse into a singularity, and the universe could not exist. In the history of physics, there were many infinities that appeared in equations and were almost always removed by a better theory of physics. As an example, Newtonian physics allows infinite velocity, and a particle with infinite velocity would have also infinite kinetic energy. Since mass equals energy, infinite energy implies infinite gravitational interaction, so that the entire universe would collapse into a point. In Einstein's theory of relativity, maximum velocity is speed of light c, and the infinity is removed. Another example is that the electron as a point particle would have no size, wherein the limit of radius r equals 0. Electric charge is contained within an infinitely dense small pinpoint, and would also have an infinite electric repulsive force, and then would also have an infinite electromagnetic energy. Since E equals mc squared, then the electron should also have infinite mass, which would produce infinite gravitational force on the entire universe. It represents a monumental paradox that cannot be resolved by giving the electron size, since the electron has spin, and if it had size, it would spin faster than speed of light. The paradox was resolved by Dirac theory of the electron and quantum field theory that shows that every particle has a corresponding antiparticle with the same mass but opposite charge. The antiparticle to the electron is the positron, and because of the Heisenberg uncertainty principle, particle-antiparticle pairs form in the vacuum, which last for a very small time before they get destroyed back to nothing. For an electron or positron, the time interval for which it can exist allowed is approximately 10 to the minus 21 seconds. Then virtual positron-electron pairs popping in and out of existence interact with the real electron, which prevents infinite energy, reducing the electric force to a measurable physical value. Infinite electrostatic repulsion and energy is screened out by virtual positron-electron pairs. Then effective electric charge decreases further away from the electron. Without quantum field theory, the existence of the electron would be a paradox. We know it is true from experiments. In general, as the space or length of the physical system gets compressed, the temperature or energy increases. A photon that has large energy has also a small wavelength, so energy can be compared to inverse length. A Large Hadron Collider in CERN has a collider beam that can achieve large energies, 13 tera electronvolts, and therefore probe very small lengths. As the length of observed space decreases with energy, some of the virtual pairs that were screening out the infinite electric charge are not in the sphere around the electron and do not longer contribute to reduction of charge. As a consequence, the effective charge of the electron becomes larger, so the charge increases with decreasing distance from the electron. At energy and temperature of the Large Hadron Collider beam in CERN, the electron charge, or more precisely, the strength of the electromagnetic force increases by 15%. For the strong nuclear force, it is the opposite. The strength of the force decreases with increasing energy. The reasons are too complicated to be included here. Eventually, all forces seem to converge to the same strength at the energy of the Big Bang, when the observable universe was the size of the Planck length. I have to say that the reduction of electric charge presented here is somewhat descriptive picture of a more complicated theory. So, the quantum field theory resolves the singularity problem of infinite electric charge and mass of the electron. Similarly, quantum gravity can resolve the infinite density caused by gravitational singularity of the Big Bang. Infinity is a place where the theory is incomplete and not a reality. In perspective, standard model of particle physics has many infinities. It was shown mathematically that for every fundamental force, except gravity, every singularity and infinity can be removed. How does gravity reconcile with quantum theory remains to be answered. At temperature and energy of the universe now, gravity is weak compared to other forces. Actually, it is 10 to the power of 37 times weaker than the electromagnetic force. At the moment of Big Bang, when temperature was 10 to the power of 32 Kelvin, at the length scale of 10 to the power of minus 35 meters or less, quantum gravity effects are important, and strength of the gravitational force is comparable to other forces. Physics has evolved from the old idea that Big Bang was a singularity. Big Bang singularity as an infinitely dense point is a place where our theory of the universe fails, and it is based on 1960s general relativity classical theorems by Stephen Hawking and Roger Penrose. Einstein's theory of general relativity is a classical theory, and quantum physics supersedes classical physics. Stephen Hawking since then had been working on other theories of the Big Bang and quantum gravity without singularity and had some nice ideas, especially theory of Euclidean quantum gravity. Penrose also has a theory of the Big Bang called conformal cyclic cosmology that does not have a singularity but relies on that every particle at the end of the universe must be a relativistic boson. Since a massless boson like the photon traveling with speed of light does not experience time, a conformal transformation can be performed that contracts dimensions of space at the end of the universe, starting another universe. As an example, how Big Bang singularity can possibly be resolved is by noting that Penrose-Hawking theorem for existence of singularity and infinite density is valid only for matter with a certain energy condition that requires that the energy of the field is larger than the pressure. Cosmological constant, vacuum energy, and a scalar field, like the Higgs field, can have negative pressure equivalent in magnitude to density, which causes acceleration of space or inflation. There are many other options, including other quantum fields or exotic matter. So the problem is not lack of theoretical ideas, but inability to test them and perform experiments at the energy of the Big Bang, which would, with today's technology, require building a circular particle collider the size of the solar system. Would it be even wise performing such an experiment in the solar system, since it would produce microscopic black holes? Perhaps it would be a better idea performing the same experiment in vicinity of the nearest astronomical black hole, which is approximately 1000 light years away from Earth. Quantum physics has a serious measurement problem and a lack of interpretation. It is at odds with the classical view of the world, but it does resolve paradoxes that are far worse and that cannot be explained in any other way. One resolved paradox is the described infinite electromagnetic force, charge, and mass of the electron. It would be extremely difficult, if not impossible, to understand nature without quantum physics. A statement that singularities only exist in math, but not in nature, might be true. It would be almost impossible to even imagine how to measure or observe a singularity. There is a sense in which infinity could be physical. Space and the size of the universe could be infinite, or time can be infinite. As a result of many discoveries since invention of quantum physics a century ago, what was concluded is that quantum fields are fundamental and not forces or elementary particles, which are merely excitations in the field. Quantum fields permeate the entire universe. Laws of nature contain information about the existence of everything and the universe, specifically how fields and particles change and interact. Information cannot be destroyed, so even if you could destroy the entire universe, the information about the existence of the universe cannot be destroyed. In fact, a fundamental principle of quantum physics is that information cannot be destroyed. Technically, quantum physics requires unitary time evolution of the system that preserves information at all times. Specifically, of value is information about the probability of scattering events, which is the interaction between particles and fields. A test of logic. A statement can be either true or false. If the probability for it to be true is 50%, then probability to be false is also 50%. The total probability must be 100%, since all possibilities must add up to 100%. It is the law of probability, which should be valid in every universe, and even if the universe does not exist.
So we can't look all the way. We can't look all the way to the Big Bang itself. We can look some fractions of seconds after the Big Bang when the laws of physics spring into existence and we have the beginnings of the interactions between matter and energy.
The idea that law of probability comes to existence, or that it does not work for the Big Bang singularity, is illogical, because it is valid even if there is no material or physical reality. Quantum physics is dependent on the same law, as all possible ways that a quantum particle can scatter have to add up to 100%. Or posed in a different way, probability of all the possible states that the system can be in have to add up to 100%. Consider an example. An electron that has a determined spin in the direction of x-axis, when measured in the direction of z-axis, has a probability of being in the up state 50% and the probability of being in the down state 50% along the z-axis. If the same electron would collapse into a Big Bang singularity, it would be squashed beyond recognition into an infinitely dense point where the information about its state would be lost. The same is true for any other system. It would be impossible to determine whether the statement is true or false, or whether the law of probability is still valid. Some kind of mechanism has to exist that prevents such nonsense from occurring, and it's called quantum gravity. But we do not have it yet. As described, singularity is a point where our understanding of nature fails, where we require a better and more fundamental theory. Particles carry information, and at an infinitely dense Big Bang point, it would be impossible to evolve the system in such a way that would preserve information about every particle or a quantum field. Potentially, various paradoxes could ensue, such as infinite forces, time travel, and loss of information, as there would be no way of preserving the law of probability in a singularity. Infinite force would imply infinite probability of interaction, which defies logic and common sense. According to law of probability, the total probability for interaction cannot be more than 100%. Loss of information at singularity would be not just unphysical, but completely illogical and paradoxical. People working on the problem of gravitational singularity are testing the Einstein's theory of general relativity, so we can know where the theory fails and how it can be replaced by a theory of quantum gravity. Every system, including the universe, wants to minimize the potential energy. Like the skier moving down the mountain, the quantum fields want to be at the lowest point of potential energy in the valley. The universe actually wants to minimize the integral action S, which is the integral of kinetic minus potential energy. It is the principle of least action. From the action, the proper minimal path can be derived for the physical system, whether it is a skier or the entire universe. According to principle of least action, for the system with no potential energy, the minimal path for a particle will be a straight line, which can be derived using just common sense. Could there be another universe where the same is not true? The alternate universe would be not just unphysical, but illogical. Certain laws might not be valid for every universe. As an example, law of elasticity requires condensed matter and is not valid in a universe with only radiation and relativistic particles, as would be no material. String theory has 10 to the power of 500 vacuum solutions at least, and each could represent a different universe. So there could exist other universes, but each should support existence of quantum fields and forces. Further, law of probability and principle of least action should be valid in every universe. Quantum physics has clear rules and principles which define the theory.
Right, so that's the problem with modern scientists. It's like, are you Newtonian or are you Darwinian? It's like Newton, he's wrong, by the way. Right, we already know that because Newton's only a subset of Einstein, let's say. And God only knows what the whole quantum thing is going to end up being. We don't even know how to structure our thought in accordance with those presuppositions.
I add to previous comments on Jordan Peterson's ideas on quantum theory and science. Quantum physics suppositions have structure as a consequence of principles of quantum mechanics, observable properties of nature that can be measured in an experiment or during observation are real. and can only be known with a certain probability. Further, information during evolution of the physical system, including the information of the entire universe, cannot be destroyed. If information can be lost at singularity, quantum theory and physics would fail. Another rule of quantum theory is that a particle is represented by a quantum wave function, which is a probability wave in space. In a sense, the electron is screened out by a probability cloud of virtual particles that reduce the infinite charge and energy. So the electron is in principle a cloud of probability described by a quantum wave function and only has properties of a point particle in the moment of measurement, when the wave function collapses to a definite, measurable value. The limit on precision of the position of the particle could be the Planck length, as the measurement at Planck energy would produce a microscopic black hole. At the end, it is clear why Albert Einstein was wrong when he claimed that quantum physics is incomplete and that every particle has a precise location, which cannot be implemented in practice, as it would probably produce a paradox of infinite charge and mass. It was Einstein's theory of general relativity that led to discovery of the Big Bang singularity. But it is a mathematical failure of the theory. It represents our ignorance and the point where our physics models break down. Until we have a complete theory of everything, it is virtually impossible to exactly understand the universe at energy of the Planck era, where the Big Bang singularity seems to appear. All of it is a consequence that we do not have a theory of quantum gravity, so we just do not understand infinite solutions in theory of general relativity, which is not a complete theory of gravity. Physics is almost always more complicated than our mathematical models. Throughout history, with every century, more advanced models were developed that better describe nature and reality. Are we at the end of evolution of science? Definitely not. I just demonstrated how to study and understand physics like a real scientist. Hopefully, it is more clear what science is and what is not, and the difference between mathematical abstract ideas and physical reality.